Thank you for this kind introduction. It's for me a pleasure to be here. I enjoyed many times my visit to Sao Paulo and other places in Brazil. But today I'm supposed to make the formal introduction to quantum gravity. So quantum gravity is a very challenging subject, which we don't know yet what is the solution to this challenge. But there are several steps forward, and I will show you some approaches to quantum gravity which are, let's say, not completely discarded. But let me start saying that, first of all, I will not be able to talk about many successful approaches to quantum gravity which other people are following. In particular, I will say nothing about the functional exact normalization group approach, which is asymptotic safety. Not about string theory, which is another approach which contains quantum and some gravitational sector. ADS-CFT duality, there is a misprint in this slide, but you understand what I mean. Nothing about loop quantum gravity, which is a completely self-consistent approach to quantum gravity. Posets approach to quantum gravity. And also non-commutative space-time approaches. So there are too many approaches, and I will follow none of those. Let me just start saying that gravity is a special interacting field by several reasons. One, gravity is the first interaction that mankind discovered. There is written in the Bible that with the sweat of your brow you will eat. So it means you have to fight all your life against gravity. In agriculture times, you have to work carrying waste and many other things. So essentially, you spend energy in fighting gravity. Also, not talking about transportation after the invention of the wheel, you can pass hills and something where you can escape the problem of gravity. So we know gravity since long time ago. But also, modern science started from gravity. Galileo was looking at the plane, the interaction with the terrestrial gravity, to distinguish between inertia and forces, which is an artificial distinction because inertia is the coupling to gravity itself, and the rest can be another interaction. But anyhow, it was the basis of development of modern science. And then the second step was given by Newton, who formulated the universe. The first quantitative approach to a fundamental interaction in nature was gravity. It was made by Newton when he discovered the universal law of gravity, which allowed to identify the attraction of the planets to the sun with the Earth gravity. Later on, other interactions came into the game. The main one was electrodynamics. Electrodynamics was the most successful interaction for physicists because it's the interaction which allows us to survive nowadays. So what happened with electrodynamics, which was discovered by famous people in 2 centuries ago, the law which allows us to jump from the macro world to the micro world was electrodynamics. There is a rule which says that the owner of the machine is the owner of the production. And this is what happened with electrodynamics. Physicists start to understand the laws of electrodynamics quantitatively too. And once they have the machines to accelerate electrons, they were bombing matter with all these charged particles. And you know, classical physics was the science of the microscopic. The microscopic part was for chemistry. But the use of electromagnetism allowed to jump inside the atoms, and since then, all this subject is on the realm of physics. Okay, but this is not gravity. So still gravity is kept as a traditional fundamental interaction, the first one we have, and then electrodynamics. Apart from these two interactions, all the rest of interactions which appear in the 20th century, strong, weak, and everything else, they are purely quantum. They have no classical analogs. They are described by quantum field theories. We also learn how to understand electrodynamics from the quantum field theoretical viewpoint. That's true. So, but there is also a meaning of classical electrodynamics, which is the most successful part of the progress in physics, as I mentioned. So, so the question which remains is gravity following the same rule? Our understanding of gravity is purely classical. So is it possible that there is a quantum part of quantum gravity, like in electrodynamics, where you have both classical and quantum? This is the open question I will try to address. So try to quantize the successful theory we know of classical gravity is one approach, but there are a few essential differences from gravity and all other interactions. The first one is that gravity is always attracted at short distance. This has to do with the fact that gravity is described, as we will see later, but a particle of helicity 2, which is the graviton. The fundamental particle is a graviton. Even at the classical level, this is what happens. So helicity, for massless particles, instead of spin, we have helicities, well, which is the similar thing, but for massless particles. So you have helicity 0, is a scalar field. Helicity 1 is the photon and all gauge fields. Helicity 2 is graviton. And all even helicity field theories are attracted at short distance. Whereas odd helicity, like electromagnetism, can have both signs, attractive and repulsive. But the even helicities can only have one sign, attractive, at short distance. This is one difference. The second difference, which is fundamental, is that all matter in the universe interacts with gravity. So there is no hiding. There is no Faraday places where you can isolate the system from the radiation outside. For gravity, there is no such a cluster where you can isolate a body from interacting gravity. You can do it artificially. You have these flights where you have zero gravity and so on, but this is instantaneous and is, you use general relativity to take it at some points, absence of gravity, but not fully, right? So this is very important. All bodies feel gravity. So if you quantize gravity, it will affect the whole universe, all other bodies, because they interact with gravity. So the second consequence of that, they interact with gravity because in the Einstein formulation of gravity, the field of gravity is a space-time metric. So, and this is a fundamental ground for all field theories, because all field theories are defined on a space-time background. If gravity is moving that background, it affects everything. If you quantize this background, it's not clear what will happen to the other fields. So this is the major concern with quantizing gravity. There are other important consequences of the fact that gravity is universal, but let's postpone the presentation of this part. So I also have given some problem sets which will appear on the slides, but will be on the web page. So you can take the problem set from the web page. There are essentially two sets, one for the first lecture today, and another one for the second lecture, which will be tomorrow. So here is the bibliography. So reference, which may be useful for you. They are also on the web page. And there are not many. I put just the essential ones, which allow you to follow part of the lectures, but you can take it for back home analyzing. So let's start with the classical theory of gravity. The most successful theory of gravity is not Newton's. One is the Einstein's approach to gravity, which also keeps universality. So Newton made the jump from the Earth gravity to the solar system. But Einstein made the jump of gravity, universality of the gravitational interaction from the solar system to the whole universe. So the scope of Einstein is very impressive. And this theory is formulated in terms of space-time metric. You see, for Newton, even if you formulate it in field theoretical language, there is only one field, scalar field, one field, which is responsible for the 1/r interaction. Einstein made the jump to 10 fields. Metric has 10 degrees of freedom. Why you need 10 degrees of freedom to solve a small problem, which is, let's say, relativistic invariance? So the Einstein argument is that all interactions should propagate at the speed of light, cannot be instantaneous. And this cannot be formulated, Newton's gravity cannot be formulated on that language. So to accommodate gravity interaction to the relativistic principle, you need 10 fields. So the action he wrote a bit later than Hilbert was the Einstein action, which is proportional to the curvature of the space-time metric. Here, this G is minus the determinant of the metric tensor. And so with this action, this is the Planck mass, which in Gabriel lectures was 1/k² yesterday. But nowadays, we add to this Einstein original action, which was responsible for the explanation of the Mercury orbit precession of the perihelion, and also for the deviation of light in the eclipse, take it in the year 1919. But the rest of the applications of the Einstein theory for cosmology are, to accommodate to cosmology, you have to include this term, which is the cosmological constant term, which is exactly, is similar to the Einstein term, but without the curvature tensor, scalar curvature tensor. So this was also formulated by Einstein to find solutions of the equations of motion of this theory, which were compatible with his idea of a static universe, right? But nowadays, this constant has been recovered not to give rise to this cosmology, but the opposite one, to expanded, accelerated expansion of the universe. And so with this simple Lagrangian, you explain most of the current gravitational interactions, except that there is matter and other interactions again, you have to add to give a complete description. But from the pure gravity viewpoint, this is the successful model. It goes from microns to cosmological distance. So this is the theory we need to quantize. But the first question that appears is why to quantize gravity? Is it necessary? Maybe, gravity is just pure classical. We don't know why we need to quantize. Well, there are several reasons why people insist in quantizing. The first one is that these theories, even the Einstein theory, is plenty of singularities. Solutions of Einstein equations are plenty of singularities. That was shown by Penrose and Hawking. You have singularities which are associated to black holes, let's say static solutions where localized matter in a short region of space. And also, we have singularities in the time evolution, which can give rise to existence of a Big Bang or a Big Crunch. So there are many, many singularities arising from Einstein equations. Also in electrodynamics, you have some singularities. In fact, there is a connection between the classical singularities of field theory and the UV singularities in the quantum theory. They are not independent problems, because essentially the mathematics you use in both cases is quite similar. But the second reason why to quantize gravity is because we expect that all interactions should unify, because so far this unification program was very successful, and strong and weak interactions were unified with electromagnetism in the standard model. So they are described as a unified model of the whole set of fundamental interactions, including the Higgs field, which now we understand that is a fundamental field too. But gravity is outside this picture. So if you want to unify all these matter models with gravity in the same footing, you have to quantize gravity, because otherwise it's impossible to unify. Because the matter, you cannot give up quantum physics. In fact, there is another reason why this have to happen, is you can ask yourself why the electron is not a black hole. Electron is point-like. Any point-like particle is a black hole in Einstein theory. And if electron were a black hole, there will be no electromagnetic interaction, because inside the horizon, you cannot say anything. So why electrons interact at short distance? No. Reason is that the electron is a quantum particle. And the uncertainty principle does not allow to have a point-like particle static. Okay? So fortunately, the electron is not a black hole. So you cannot escape for quantizing. It's compulsory to quantize matter in the presence of the singularities of gravity. So why not to quantize gravity itself to explain this? So then, here is the main motivation for me is that the resolution of the UV problem is incomplete if you do not quantize gravity. This was a question not raised in these terms by Einstein, Albert Einstein. Einstein finished his program of classical relativity before the 1920. And the rest of his life was working on unification of gravity with the rest of interactions, essentially electromagnetism. Why? Not by some artificial reason. It was a fundamental one. He was scared of UV divergence of electrodynamics, which is a real problem. It's not the Landau problem you have in quantum field theory. It's a classical problem. You have a singularity in electron at short distance has a singular interaction. And one way of escaping of these singularities, which is, as Einstein said, well, Einstein have not said that but God doesn't like singularities. Einstein did not say that, but some similar expression. So it cannot be a complete field theory have to be without UV singularities. And he thought that the solution of the electromagnetic singularities will be the interaction with gravity. And this was also the reason why he didn't like the the fact that gravitation has gravitational waves. Because if you have gravitational waves, you have singularities. So even if he discovered gravitational waves in the early 19th, in the late 90s, he tried to kill that in the 40s, unsuccessful, of course. So, but the main reason is that gravity can explain why we can get rid of these UV singularities, not in gravity, but in the whole quantum field theory setup. And the last reason to quantize is that there is a fundamental problem in the standard model. The standard model is very nice. It describes the physics, particle physics very precisely, but it's unstable. So here you have the quartic effective coupling of the Higgs as a function of the scale, of renormalization group scale, is running, right? And the problem is that if the mass of the set at this plot is in here, which is more or less where it is now, you are in a region where the sign of this coupling is negative. If you have a lambda phi 4 theory with negative coupling, it doesn't make any sense. So there are problems in the standard model if you take it without interacting with gravity. And perhaps the interaction with gravity will solve this short distance problem, which is at very high energies. You see, we don't have to care too much because it's a very large energy. So here is the Planck scale, but we are far beyond what LHC experiments can show us. So this is the last reason. So let's try to quantize, okay? And what will be the realm of this new theory of quantum gravity? I mean, of course, singular scenarios, which are the pre-inflation physics, primordial black holes, which in this scenario can be created and will interact with the cosmic background radiation, giving rise to B modes. Black hole physics, as you know, according to Hawking, when you put the interaction of classical gravitational theory, Einstein theory, with quantum field theory, for instance, electrodynamics, you know that even black holes can radiate. It's the Hawking radiation. This is very small radiation. It's very weak. But if you have a very small black hole, they lose energy by radiation and can evaporate. The full description of this system requires quantum gravity, because otherwise you violate information loss. You have information loss. So, okay, this I already did. Well, there is another special property of gravity with respect to electrodynamics, is that the interaction of gravitation is much weaker, 10 to minus 14 times weaker than the electrodynamical interaction. So the effects will be much weaker in particle physics. This is why we usually don't take into account the gravitational field in particle physics of accelerators, because it's irrelevant. Okay, so let's start to quantize. So how we do quantize? There are many methods of quantization. I will follow in this first lecture the canonical approach. Canonical approach breaks covariance. It means that you have, let's do it first for classical scalar field theory, where you have a scalar field. I take it real, so you have this kinetic term, some potential, which can be any functional local dependence on the field. And this is the classical Lagrangian in canonical coordinates. You have a space-time in Minkowski background, so you have a special direction for time and a special direction for space coordinates. So these covariant derivative terms split in two parts, one which we call kinetic, and the other one which is just the space anisotropic contribution to the Lagrangian coming from the scalar field. So if you have such a theory, you can follow the canonical approach at the classical level. defining the momentum associated to the field. This field depends on space coordinates. It might depend on time too, but a fixed time, it depends only on space. And the momentum is the functional derivative of this Lagrangian with respect to phi dot, as in classical mechanics. This is the canonical momentum conjugate of 5. According to this transformation, if you perform the Legendre transformation, you get the Hamiltonian. There is a kinetic term, which now is expressed in terms of the linear momentum. Now there is a flip of sign of this anisotropic, special anisotropic term, and also a change of sign of the potential. Okay? So this is the classical Hamiltonian associated to the scalar field theory. In the problem sets, there is an alternative derivation of this Hamiltonian and also the linear momentum. This is the canonical momentum, but there is also linear momentum. And the first problem set is to derive the energy momentum tensor of this theory, and the 0,0 component should be this one. And the 0I component will be the linear momentum. So this is the problem you have to address. So it's a short way of deriving the Hamiltonian without performing Legendre transformation. In some cases, it's much more powerful. This was the Schwinger approach to field theory, classical field theory. So the canonical quantization, you have to accomplish the Heisenberg principle that the canonical momenta and the field have to satisfy this conjugation, these commutation relations. It should be an I, H bar, but H bar I will take it for 1. I mean, I have a, remember one professor when I was much younger, much younger, he used always, you know what is known as natural units, right? Natural units. This one, you are familiar with this choice. But he was using what is called supernatural units. Okay, so you never make a mistake in supernatural units. I hope I made no mistakes too in the slides, although they are unavoidable. So here you have to satisfy this, I mean, you have to realize in a quantum Hilbert space, this is definition of field theory. You have a quantum Hilbert space, as in quantum mechanics. You have a representation of Poincaré group in this Hilbert space by unitary operators, or anti-unitary in some cases. And then the generators of translations of rotations are self-adjoint operators. The generator of translations is the Hamiltonian. Space translations, time translations. The space translation is the linear momentum. And all other generators have the same representation in the Hilbert space. But what is essential for quantum field theory is not the fact that you have a representation of the Poincaré group, which is, of course, there is a problem with Lorentz transformation because you are working in fixed time, but I mean, this can be solved. So, for the generators. For instance, the Hamiltonian is well defined, but time translations, a fixed time is not well defined because you have to jump from one time to another. But apart from this subtlety, you have this. But the important property is not, the most relevant property is not you have a relativistic system. The most important property is that there is a fundamental operator in the theory. And this fundamental operator is the scalar field, in this case. So, quantum field theory is a quantum theory with relativistic invariance plus the existence of operator in the Hilbert space, which is the quantum field. The field theory depends on what you choose as fundamental field. If you don't specify the fundamental field, you have not defined the quantum field theory. So, and the commutation relation, this quantum field operator has to satisfy with the other operator, with the canonical momentum conjugated to the field, is this one. One particular realization of this quantization is take as Hilbert space the space of functionals of the fields of time fixed fields. So a space like fields, any functional like this one is if it is with a proper inner product defines a Hilbert space, and in this Hilbert space, the Hamiltonian or the canonical commutation relations can be defined by with the field as a multiplicative operator because acts on functions of the fields by multiplicative operation, and the momentum is the functional derivative with respect to the field. Of course, you can verify that with this prescription, this law is immediate. Okay, so the Hamiltonian is obtained following this rule. You have in the previous slide here the classical Hamiltonian. You have to replace phi for operator, which doesn't commute with the field, and this is the operator which doesn't commute with the classical field. So you have this, a Schrödinger-like operator. It's like a Schrödinger Hamiltonian, but in an infinite-dimensional space, the space of all functionals of the classical fields. So the quantum states are functional of the classical fields. And so here is the quantum operator, including a particular choice of the potential. You have a mass term, and you have a self-interacting part. So this is a well-defined operator in the space of functionals of gauge of scalar fields. The vacuum state is in the case where you have no self-interaction, is given by this functional. This is a particular choice of the functional with a normalization constant here, but this is a Gaussian. It's a Gaussian functional of the classical fields, time-fixed classical fields. You can verify by plugging this in, apply this operator to this, and with p equal to m square halves of phi square, and immediately you will see that this is as eigenstate of this Hamiltonian. The problem is that this n is divergent. If you want this integral, to be a normalizable state, you have to have here a divergent prefactor. So this is the first UV divergence that appears in this quantum field theory. The second one is the eigenvalue you find is this one. So the vacuum energy is the trace of this operator, which is a pseudo-differential operator, and it turns out that this is divergent because essentially this delta has eigenvalues which is k squared. So k squared plus m squared, if you integrate over k, is divergent, okay? So this is the second divergence which appears in the theory. And that's all, no more divergences. So in this case, you can renormalize the theory just by removing, so just by considering this divergent constant, removing. And the second, you just subtract the energy of the vacuum. So the Hamiltonian is the one in the previous slide, but you subtract this constant term, and the rest of the spectrum of the Hamiltonian becomes finite. So the theory is self-consistent. If you have a mass, and you have a coupling, quartic coupling, phi squared, then it turns out that this mass gets also corrections, which are divergent. And also, the same happens for the coupling term, phi lambda squared. So this means that the Hamiltonian was well defined by when you have interaction, the theory needs some renormalization, and renormalization can be achieved by changing the Hamiltonian just by absorbing some divergence in the definition of the scalar field here in the anisotropic part, in the mass term, both in the mass and the field, and here both in the coupling and the field. So you can absorb all divergences in the Hamiltonian. The Hamiltonian looks the same, and now this Hamiltonian taking it as the original Hamiltonian, you get as an effective Hamiltonian the one I wrote before. So everything is finite in this model if you follow this prescription. The only problem is that the corrections to this lambda 0 term, you have to update it at any order in perturbation theory. It's the only problem. But the theory is self-consistent, and there is a small problem which has to do with the non-perturbative approach to this theory, but let's skip that for the moment. So let's go to a more complex system, which is gauge theories. In gauge theories, you take Young-Mills theory, and you have, this is the Lagrangian for gauge theories. F mu nu is the curvature of the gauge field, d mu a mu plus minus d nu a mu plus the commutator of a mu a nu. So you compute, you write this in the canonical formalism, splitting times and space. Again, you have a kinetic term, now with some additional contribution from the A naught potential, gauge potential, plus the space-like. So this is, in electrodynamics, this is the electric field, what is inside this bracket here. And this is the magnetic field square. So you have the electric field square minus the magnetic field square, which is the classical electrodynamic Lagrangian. So if you, again, compute the canonical momentum, which is the derivative with respect to A dot, you get that this is 1 over 2g squared. G squared is the coupling. You get times the chromoelectric field, which is this. But if you do the same for A naught, since A naught has no time derivatives, you find 0. So this is a constraint. This system is not like the scalar field. It's constrained. You have a constraint. And even more, if you want to have this constraint stable under time evolution, you know, the Heisenberg equation for the evolution of pi naught is to take the derivative of the Lagrangian with respect to A naught. Okay, this is the Heisenberg equation for. So the derivative of this Lagrangian with respect to A naught gives me this term. And so this should vanish in order to keep this primary constraint stable under time evolution. And this is the secondary constraint, which is called Gauss law, which in case of electrodynamics is the responsible for charge conservation. This is the Gauss law. It's the first Maxwell equation. Because this is the electric field, you have no covariant derivative, it's just the divergence of the electric field is equal to 0. We have no matter, no charge, okay? So the Hamiltonian, you can proceed the same way. You have the classical Hamiltonian, which is this one. And if you quantize with the same prescription, it's Schrödinger-like prescription. Now you have the commutator relation. There is a Kronecker delta between the components of the gauge field and the canonical momentum. And again, you get a very nice Hamiltonian. It's a Schrödinger-like here. Infinite dimensions, of course. This is the Laplacian in the space of gauge fields, space-like gauge fields, times the magnetic field square, which is well defined for any gauge field. But then you have to remember that you have to accomplish the Gauss law, which in this under this quantization prescription tells you this. This should be 0. Any physical state. So this Hamiltonian is defined on the set of physical states which satisfy this constraint, Gauss law. What does it mean, this constraint? It means, I will see in the next slide, that the quantum states, which are functional of the space-like A potential, vector-like potential, is gauge invariant. Physical states should be gauge invariant. Let me show that. If I have a gauge transformation, the gauge field transforms. So gauge transformation is a mapping from the space-like, so this is R3, into the gauge group, okay, G, SUN, for instance. Then the definition of gauge transformation is that the transformer gauge field is just this combination, which is covariant transformation, times this inhomogeneous term, which is the gradient of the field. So in infinitesimal terms, if you take 5 as exponential of delta 5, this reduces to, but infinitesimal variation of the gauge field is given by this covariant derivative of the infinitesimal transformation, gauge transformation. If you apply to the original gauge state, physical state, you make the derivative with respect to A and multiply by the variation of A with respect to the variation of the gauge transformation. And so integrating by parts here, this term passes here, and you get the Gauss law, which goes here. So the meaning of Gauss law is that all physical states should be gauge invariant. So this means that these functionals, which were functionals of the gauge fields, have to be functionals of the space of all three-dimensional gauge field modulo the space of gauge transformation. So you have A here, you have the gauge orbits. This is the space of all gauge fields. You have the A5, and the whole orbit, the function of the physical state is constant. So finally, you reduce your physical space to functionals which are defined in the orbit space. The space of orbits of the gauge fields. And in that case, you remove the Gauss law. If you consider just fields which are defined on this manifold M, which is infinite dimensional manifold, but smaller than the original one, the gauge fields, then you have down. So that's the full Young-Mills theory. Then you can gauge fix and perform perturbative calculation as you obtain something equivalent to the standard covariant approach. Let's go to gravity, which is the topic, main topic. So we do the same. Canonical approach. This is known as Arnovit-Desser-Misner approach to classical gravity. And you can find explicit development in the bibliography I gave you at the beginning. Then you split your line element square into several pieces. First, so this is just G mu nu, dx mu, dx nu. Okay? This is what is this. So you split in the time part, which is dt square, because here is chosen the prescription that the time derivative is with minus sign and the space derivative with plus sign. Sorry, the space metric with plus sign. So you have a pure timeline term, which you call n squared, the coefficient in front, which is known as lapse function. Then you have the space-like part, which has two components, one which is gij with dxi, plus some time component, and the same in the second factor. So essentially, this gives you that the time dt squared, effective square, is minus n squared plus ni squared. Ni is what is known as the shift factor. So this is the most general expression for any metric into space-time of the form R times any space-like space M, which can be R3. But then the only problem here is that you have split the time component in two pieces, one which is n squared and the other one which is ni squared. And the mix of terms are the ones you have. Okay, so by using this decomposition of the metric, which in the gauge case was simpler because it was A naught dt plus AI dxi, much simpler. Here you have to do it in this way. So you can split the Einstein action with cosmological term in this way. You have as fundamental coordinates metric, three-dimensional metric. These are the real degrees of freedom. Time derivative of these three-dimensional metrics, and the lapse and shift function coefficients. So which are space-time dependent functions. So they vary from point to point. So the explicit form of this Lagrangian is this one. Well, you have the mp squared, the Planck mass squared, or if you wish, the Newton constant term. And then you have a common factor, which is the lapse function, the square root of j. You see, this is the space-like metric, which I take it positive. And then Kij, which is the extrinsic curvature, which I will show you in a moment what it is, plus the three-dimensional part of this R and this term, which is the same, because you only have the integral over the space part of the space-time. It's a fixed time prescription. Here is the definition of the extrinsic curvature. It's the time derivative of the metric plus the covariant derivative of the shift functions symmetrized, modulo the lapse function. So this is definition you have learned when you have these lectures on curves and surface in elementary courses of the degree. There you have the extrinsic curvature definition, which is, in that case is for surface in 2 dimensions, and is exactly this one. So we have splitted the action into one kinetic part plus some space-like parts, like in the gauge theory's case, and also in the scalar case. But there is another way of writing the same thing, which is, so using our configuration space is the space of all space-like metrics. This is the configuration space. You have time derivatives of these metrics, and you have curvatures and many other artifacts, extrinsic curvatures, and so on. So this is the space. Then you have the tangent space to this space, which is this G dot plus so this is the velocity space. And then you have the cotangent space where you have three-dimensional metrics and the conjugate momentum. But then you realize that in the space of the configuration space, there is a product, a Riemannian product of the metrics, which is given by this, the W metric of metrics. So it's a product in the space of metrics. Given two metrics, you can define the product of these two metrics according to this. Here we choose the kernel of these metrics, you know, the product of these two metrics. Is what is written there. So this is a special metric which is well defined in the space of metrics. Yes? Well, the index are down, but you can put it up. Yes? The metric is this one. This is the kernel of the metric, but it's the same notation you use when you say that the product of two vectors you call it metric to this or to this. Properly speaking, you should call it to this, but you can also call to this the metric. And here is the same. This is the real product, and this is the kernel. So you identify the notation. No, no, no. You are right. No, I understand. I understand your point. This metric is defined on the space, let's put here, on the tangent space of metrics. And this one, which is there, is the point where you evaluate this. So you have a metric here, which is Gij, and then you have two vectors, which are these dots. Understand now? Okay. So this is the background metric. So you are in a fixed point of the space of metrics, and you define, because the product is only defined in linear spaces, okay? The metric space locally is linear, but globally not, because you have to preserve, for instance, positivity and all the properties of the metrics. So this is the correct understanding. So the metric is this one at the point G, but it changed from point to point. So, but using the notation becomes very useful, because then the kinetic term here, and this part too, can be written just as a pure, so this is the second factor, which appear like K scalar, the scalar of the extrinsic curvature. And so you have the kinetic term here expressed in terms of this metric of metrics, and then the trivial three-dimensional reduction of Einstein action. This is the three-dimensional Einstein action. I keep the same notation, sorry, for R and R4, but it's clear from the context that this is three-dimensional. So you have also some external pure derivatives, which are not relevant because they are boundary terms in the theory. So now you have to analyze classically this system before quantizing, and you have, as we did in the case of gauge theories, you have to compute the canonical momentum associated to the lapse and shift functions. And since there are no time derivatives here, you know, lapse function and the shift functions have no time derivatives, so both momenta are trivial, zero. Constraints. You have to impose by force that these momenta are trivial in the phase space, which is here. This is the phase space. So I just wrote the part of the phase space which depends on the metric, but you should add to this also the part of the phase space which depends on the lapse and shift function. But then you have a secondary constraint. Okay, you also compute the canonical momentum associated to the metric, which is this one, and it turns out to be this expression, which depends on the lapse function and also the extrinsic curvature. It's the equivalent as in the case of gauge theories. And then, if you want to keep these constraints, you have to impose these two constraints, which are secondary. They are derived from the primary constraints. The first one is telling me something intricate, which is like this contraction of the width metric with the canonical momentum minus this should be zero, and the second one is this one. This is an obscure. It's a mathematical derivation. You can work yourself, because I will skip it because it takes some time. But then it's very easily to understand why they, and what is their meaning, and why they should be here. This term is nothing but the Hamiltonian up to the lapse factor in front. So this constraint means that the Hamiltonian should be 0. Let me finish. I will come to that. And the second constraint here gives me, well, let's keep it like that, okay? But the Hamiltonian is, so you see the second constraint is here too. So if this vanishes, this term will vanish too. Which was your question here?
On the definition of Kij on the first equation there.
Yes.
See a covariant derivative on the lapse function.
Yes.
Is it a gauge covariant derivative?
No, is the gravitational covariant derivative. Is with the Christoffel symbol of the three-dimensional metric.
I didn't understand the symbol. I thought it was a gauge covariant.
Sometimes people are writing this as nabla instead of D, okay? If you are more happy with nabla, you put it nabla. Is the covariant derivative. Here we don't have gauge fields, okay? Just pure gravitation. It's enough. It's not good to complicate the theory. So we have an understanding of what is the meaning of this constraint, which can be derived immediately from motion equations and this definition. So, and what is the meaning of the second one? The meaning of the second one is that the linear momentum of this theory is also vanishing. But this you should expect from the very beginning, because we have the Einstein theory was diff invariant. By diff, in that case, I mean space-time diff invariant. So diffeomorphism in 4 dimensions. Here, in the canonical approach, we are only dealing with diffeomorphisms in 3 dimensions. So our Hamiltonian, this one, is invariant under diffeomorphism in 3 dimensions. It's invariant because it's gauge covariant all the way, so it's explicitly gauge invariant. So gauge by diff, diff invariant. So, but what is missing is that in 4 dimensions, apart from the 3-dimensional diffeomorphism, you have the 4-dimensional diffeomorphism. In particular, diffeomorphisms on time, which only shift time, maybe even translation in time. But not only translations, any diff on time, any change of time coordinate is a symmetry of the Einstein Lagrange action. So you have an extra diff invariance, and also the same for space-like coordinates. You have transformations which change the coordinates, spatial coordinates, but depending on time. At each time, a different diffeomorphism. So you have a diffeomorphism in the space, in the 4-dimensional space. These 2 symmetries, which are absent in canonical quantization, explain that you have to have a vanishing of the Hamiltonian, because Hamiltonian is the generator of time translations, and you have invariance under time translations in the original theory, so it should vanish. So this explains why this constraint is fundamental. And the same happens with space-like translations, because you have a space-like invariance, okay? So these 2 constraints are natural, but the theory tells me that there are no more constraints. In fact, there is a very nice derivation of the whole stuff here, which I'm not following, which is starting from the 4-dimensional theory and define the same symmetry diff in 4 dimensions. Then you have, to increase the number of coordinates here, but at the very end, you get the same result. The same for gauge theories. In gauge theories, is the same theory. The Gauss law can be interpreted as the time-dependent transformations, with gauge transformations that you are forgetting in the canonical formalism. Okay, So we have to quantize this theory, and again, you use the Schrödinger prescription for implementing the non-trivial commutation relation between the space-like coordinates and the canonical conjugate moments. Of course, you have to quantize also n and n, but since they are constrained, you don't need to add any extra term because pi naught is 0 for them. The momentum, canonical momentum is 0, so they will not appear in the kinetic part, and they only appear here, the two constraints. This is the Hamiltonian with the prescription here, and so you have a very complicated operator which acts on the functional. So now the configuration space for the quantum theory is the space of functionals of metrics where we have a Riemannian structure. So the space of metrics now has a Riemannian structure given by the DeWitt metric, right? So in this space, this operator acts naturally, so because it's a functional derivative with respect to this metric, three-dimensional one. And the rest are multiplicative factors. Well, there is a first order here, differential operator, which is acts also here, making derivatives, but which vanishes according to the constraints we have here, right? This is the linear momentum constraint, which makes this term vanishes. But we have an extra constraint which the full Hamiltonian should vanish. So the quantum theory is given by this Hamiltonian in this space, but you can also interpret this law here as saying that these functionals here are invariant under three-dimensional diffeomorphism. And here is it. Physical states should be invariant under coordinate transformations of space. So this phi star Jij is a space-like transformation, you know. In other terms, the coordinates transformations is this one, metric change under coordinates, and this being the covariant derivative. To be consistent with my notation, this should be like this, okay? And like that. So if you apply this transformation law to these functionals, you get that the variation of any functional of the three-dimensional metrics is given by this, because this is the variation of the metric, and this is the variation of the functional with respect to the metric. It's just the chain rule. Apply the chain rule. And since this is vanishing by the constraint we have previously, when you integrate by parts here, then this is 0. So it means that the variation of the functional under diff, three-dimensional diff, is 0. So this is the meaning of the first constraint, that the states should be invariant under three-dimensional diff. So the Hilbert space reduces, instead of having functions on this configuration space, again, the same picture. You have the space of metrics, where the width metric is. You have Gij, you have the phi start Gij, which is the transformed by a three-dimensional diff, and the mode space is M over diff of R3. Let's put R3 instead of M because there are too many M's. So this is, okay. This is this space, and all functionals here automatically satisfy the constraint. So the constraint has been integrated out. So we don't have to worry more about this constraint. And so all states are functions defined here. Okay? But then the Hamiltonian, because it's invariant under diff, is a differential operator on functionals in this space, which is the projection of the operator we have in the previous slide. Here is the projection of this operator down to the space. This is called moduli space of metrics. Okay, moduli space of metrics. And what happens is that this operator, which is a kind of Schrödinger operator defining the functionals of this functionals of metric of moduli space, is quite complicated. It's a nonlinear operator. You see, you have a kind of potential here, which is three-dimensional I, local one, but this differential operator is very hard to solve. Here, we don't have a solution. But the amazing thing is that the space of physical states is not the whole set of functionals on this space. It's just the set of functionals such that this operator acting on them is zero, which in principle could be just one. It's like only the ground state is a physical state. This is the strong constraint imposed by diff invariance. So, this is the final constraint, which means that this operator acting here should be zero. And this is the famous Wheeler-DeWitt equation. If you solve it, you will win the prize. But the problem is that it's completely full of divergences. So this term here is very singular. So it's not only a problem of analytically solve it, but is full of divergences. And then there are many questions. This is the fundamental equation of quantum gravity. If you solve it, you have quantized gravity. But the problem, as it happens in gauge theories, is very hard to solve the equation, first thing. And second thing, you have to solve the equation knowing the only eigenvalue that you have to get, which is zero. So it's a much harder constraint you have. So it's why this is very difficult. And so let me just raise some issues here. This wave function is called the wave function of the universe because it is the wave function which solves the quantum gravity constraints. But the question is it unique? Or maybe different solutions? Because, you know, there are some systems similar to this one, even in quantum mechanics. For instance, the Hall effect. If you solve the Hall effect, the ground state Hall effect depending on the magnetic field, can have different degeneracies. So you can have a degenerated ground state. So here, you can have a degenerated ground state. Is that the case in gravity? Well, we don't know, but we know something. This I will show later. I'm concluding. So, what is time? Because now Hamiltonian is zero, so no evolution. Exponential of IH is 1. But what is time? So there is no evolution. You have to define time. You have to redefine time to have some evolution, because we know that the universe is evolving, so what happens? How emerges classical gravity? Here is not clear. It's a very, very deep question. Then, well, this is a very, very... In the bibliography, there is a last reference. My advice is don't read this last reference to next year, okay? Because otherwise you will not come back. Because, so if you have universe, which is, you know, in quantum mechanics, there is this principle of measure. So the, you know, to know in which stage you are, you have to measure it. It's the problem of the Schrödinger cat, no? So, and where is the observer who can measure the quantum, the Wheeler-DeWitt equation? It should be somebody external to the universe. It cannot be somebody inside the universe. So this raises very deep questions about the principles of quantum mechanics. This is why very disappointing too. So who are the observers? This is the question. Should be outside. I mean, cannot be inside because they affect to the Wheeler-DeWitt equation. And as I said, this plagued of divergences, but there are more questions, more intriguing ones, which are still waiting for answers. As I said, in this last reference, you will find a lot of, not answers to this question, but more questions to be worried about. Okay? Is Chris Aishan from Imperial College who wrote these questions. So here is the problem set. I will skip it, but let me just end with some more positive. Otherwise, you will not come tomorrow to the second lecture. Tomorrow, I will discuss the covariant approach, which is nicer. You can compute things and so on. But in principle, it should be equivalent to this one. But here, you pinpoint the main questions of the theory. In the other case, you escape this question. You just compute. It's the Feynman approach to quantum mechanics opposed to Heisenberg and Bohr approach. So Feynman approach gives you how to compute and how do you evolve and so on. But the fundamental problem is not that one. It's what you measure, what are the states, and so on. And this Feynman approach doesn't give it to you. It's just a receipt to compute. And here is the same. Tomorrow you will get the receipt. So, but the Einstein, great question, I mean, motivated not by quantum, because, you know, he was not too much happy with it. Even he was the first one who applied quantum mechanics to the photoelectric effect. He was not happy with the interpretation of what is called the Copenhagen interpretation. But he raised this question, which is really deep. What really interests me is whether God has any freedom in the creation of the world. Or everything is fixed. You know, Wheeler-DeWitt equation tells you that there is no freedom. I mean, you have just one state. But now let me answer at least one question, and you can go home with one answer. Well, there is one approach to construct this vacuum, which is the Hartle-Hawking. So this is half Feynman, half canonical. So you know that if you consider infinite time evolution of any state in Euclidean approach, and thus in the fundamental state, always. Because Euclidean evolution is like this. And if you apply this operator to any mixed state, only at large times, the only one which survives is the ground state, because all others get suppressed, right? Imagine that the fundamental state you give zero energy, as we did in this Wheeler constraint, then is the only one which survives. So what Hawking and Hurler propose is that to compute the current vacuum, you start evolving from minus infinity till now by Euclidean. And even you can follow the path integral formulation, and you get a construction of the fundamental state, 5, the Wheeler state. This is the proposal by Hartle and Hawking. It's very hard to do, but was formulated in 1983. So there is another approach, which in Brazil there are a lot of people which are following, maybe some of you too, which is just simplify. Instead of considering all the metrics, just consider constant metrics in space coordinates and only time evolving. So this, the Wheeler-DeWitt equation, becomes a real Schrödinger equation in finite dimensions. And then you can solve, okay? Is phi unique? This is the only question I will answer. No. The answer is not, because there are theta vacuums. So the point is that this space here there I use a notation which is not visible in the blackboard because I'm very bad at drawing, but this space, which is the n space, moduli space of metrics, how one sees that. So it has a hole. It means that there are loops in the space of metrics, of classes of metrics, which I cannot contract to a point. Whenever you have that, you have a theta term, which in fact you can write, adding to Einstein, Pontryagin term, and motion equations are unchanged, so we could do that. But I didn't spend time because, but if you do that, you will have a different Hamiltonian and different equations or a different vacuum. But how do you prove that? To show this, it's enough to show that the space of diffeomorphism has several separate components. Because, I mean, I don't have time to illustrate. The space of metrics is, in principle, up to some singularities, is flat, so is contractible, so there is no problem. But whenever you have a group which is not single connected, like this one, this is the Bloch theorem in condensed matter. So if you have the action of a group which is discrete here in this case, which has several several disconnected components, which is set, is a spiral. So if you mod out this spiral, which was contractible, R, the whole spiral is linear, is like an iron. If you mod out this spiral by this set, you get the circle, which is, of course, not contractible. This is why. And here is the same, because the space of diff is not connected. Instead of having R3, if I assume the fields, the metrics become trivial at infinity, so diff is, let me take a sphere, S3, so compactify the space R3. The mappings from S3 to S3, which are diffeomorphism, are classified by the winding number. So I can go around several times. So the maps, the diffeomorphism in R3 are like this one set here. So the moduli space of metrics, which are orbits of diff, do have a non-trivial, non-contractible loops. And there, this gives you theta vacuum. So there are many theta vacuums here. In fact, a family, a circular family, so S1. And then each one of them has a different Wheeler-DeWitt solution. Yes? I cannot hear you. Can you speak louder? As I said, there are several options. So the vacuum might be degenerate, okay? Can have several solutions with energy eigenvalue at 0. This is not excluded. But in principle, one is expecting that apart from some boundary conditions on the singularities, well, this is a source of ambiguities. You have to fix, for instance, initial conditions and so on. And in that case, for instance, in mini superspace approach, where you approximate the space of metrics by just space-like constant metrics, there are some singular points. The Schrödinger equation, which is the Wheeler-DeWitt, has several singularities. At each of these singularities, you have to fix boundary conditions. So depending on the parameter of boundary conditions, which essentially are initial conditions in cosmology and so on, you get a different vacuum, okay? So that you have this ambiguity. But in top of that, and for me it's simpler answer, for any of them, you have this one. So even if you select one from these initial conditions, you have a degeneracy coming from this theta vacuum. Is it clear? Okay, thank you. Yes, yes. But because of the singularities, otherwise not. You know, yes.
You're talking about the space of metrics, right? Space of
Yes.
But you said yourself that there is a problem in defining a measure theory for your Wheeler-DeWitt equation. You don't know how to define the space of all possible metrics without a proper quantum mechanical way of.
No, the space of metrics is well defined and even analyze it properly. I mean, of course, there are many subtleties. So to speak properly in mathematical terms, you have to introduce some regularization and Sobolev spaces and so on. And then you are losing some properties of real physics, but you can finish this problem. So the main problem you are suggesting perhaps is the following. I have escaped one fundamental problem which is to define, which is the product on the space of functionals of this type, or in the gauge field theory case of this type. What is the product on the space of this? You have to integrate over the space of all gauge fields, or if you wish, in the space of moduli space of orbits. And here the same. Either I define a product here, I just wrote H, but for H you have to introduce a metric, and here. And this is a problem. So usually here you know what to do. You take one background state, essentially Gaussian in perturbation theory, and this helps into defining a product here. But this product then is modified, but you have a starting point. You have a product in this space, you have a Hilbert structure, and then you have to control the rest of the interactions. In this case, it's more difficult, so I escaped the answer to the problem. But in the mini superspace, you can define a product and you can try to see. But this is a huge problem. Essentially, the problem is that most of the, so you need to have a Gaussian product. So it means, for instance, in the scalar field, which is simpler, in the scalar field, it's much simpler, you use the vacuum I wrote. This. And then you can define a product in the space of gauge fields with this Gaussian measure. So it's a measure in the space of gauge field, of scalar fields. This is a measure. So using that measure, you can make the product of two functionals. But the problem is that when you take this measure, you have to modify all operators because everything was written thinking that the measure was D5. Nothing, right? The trivial one. But this trivial one does not exist because in infinite dimensions, the Lebesgue measure does not exist because you can ask yourself what is the volume of this block. And so this block, if you have L, here is L3, no? Oh, sorry. Right? But if you grow the dimension, this goes like L to N. And if N is very large, and L is larger than 1, goes to infinity. And if L is smaller than 1, goes to 0. So only if L is 1, you keep going, and independent of the dimension, you have a volume which is constant. But for a smaller one, they squeeze. For largest one, they blow up. So this is the explanation why you don't have a measure, a Lebesgue measure, so invariant under translation in infinite dimensions. But you have these Gaussian measures, but passing from Lebesgue to this one requires to change the Hamiltonian. It's a kind of Riccati. It becomes, instead of a Schrödinger equation, becomes Riccati one. But it is, can be done. For instance, in the book by Glyn Jaffe is done correctly for this scalar case. So the idea is to apply the same mechanism to gauge theories and to gravity. But the problem is that in those cases you have a lot of divergences. That is the main problem. But the problem of the measure can be solved this way. Yes. No, but the problem is the operator. To find the function, you have to solve the equation. Otherwise, I can always define a function which is finite, the constant one, okay? The constant one is perfect. No, and the constant one with the measure gives 1, because the measure is normalized. So it has norm 1. But the problem is that this constant one is not solution of the DeWitt equation, unfortunately. But here, yes, here if I take this as the product function, then the ground state of this theory is just 1. Everything changes and becomes 1 because I have to subtract the square root of that. In fact, is 1/4. So this is the way it works. So the measure is not a problem. The problem is the Hamiltonian. So the dynamics you have. More questions? Can you speak louder? Because from the back I can hear you. Can you repeat the question? Because I can't hear you. Speak louder, please. So you are working in 2 + 1 dimensions. Okay. Yes. No. I mean, even in that case, there is no known solution of the DeWitt equation. The only one is even in that case, 2 + 1, of course, this is a much simpler theory. It's almost there. Because in 2 + 1, I mean, there is no radiation. So the gravitational field, to some extent, is quite frozen. Sorry. So this theory is much simpler. And in fact, it can be solved in a different approach. You can follow the Taussig-Achúcarro approach, which is you can formulate the Einstein theory with cosmological constant in terms of Chern-Simons theory. And Chern-Simons theory, we know how to quantize. And in that approach, you go to the end. But the connection with the DeWitt equation is more involved because you still have divergences. Yeah, the module is but nevertheless, it's infinite dimensional, even in that case. So it's simpler, but not that much. What is nicer in that case is we have much more topological information about this space. We know everything. No, the Wheeler-DeWitt equation is a dynamical equation. So even if the module, like the Q space, or even this space here, have a nice structure, the Wheeler-DeWitt equation is functional equation in this space of functionals there. So there is no explicit solution, as far as I know. But in the other approach, which is there is a paper by Witten who starts saying there are two kinds of people, physicists. The ones which believe that gravity in 2 + 1 is trivial, and the ones which believe that is inconsistent. So you cannot find a middle in between. But anyhow, I think that the Chern-Simons solution is very, but I will not follow that approach. It will be more covariant. Maybe tomorrow we will see a bit more about that. Thank you for the question.
Superspace quantum cosmology models. And one thing that we look for is how to define time, how to define where our cosmology is evolving to. But all the same, in the beginning steps, we define our Hamiltonian in according with a Lagrangian that has a G, I, G, if with a G dot. What the hell is this dot? Then I will define my time in terms of this G the momentum of my metric, and then it becomes my time parameter. That always seemed like a weird thing to do, because classically I begin with an integral from minus infinity to infinity in time, but inside there is something that will, in the end, define the way that time evolves from. How do I make those two things work?
This is a deep question, as I told you. I mean, definition of time, it was open here. You have to read this last reference by Chris Ashan. You already read it, and you understand it? No. So, but let me just make more confusion. So, one problem which was mentioned yesterday by Gabriel was the problem of breaking of causality, right? Causality here, in this formalism, let me just write it for a scalar field. So now I'm talking about quantum field theory in the concept of quantum gravity. Well, it depends on how do you define the sign. Let me put it like that, and then I change the metric according to. Do you understand? So if you have points which are causally disconnected, so it means, for instance, if you have time and you take two space-like points, so 0 component here, 0 component time here, so there are space-separated points. There is no information which can travel to one or to the other. So causality says that this in the quantum level should be 0, right? This is in the covariant formalism. I'm advancing. So, but what is the meaning of that in quantum gravity? Because I have diff, and diff might change the causality of this X and I. So this, in fact, what happens is that this you cannot say for any point. So it is blown up. So it doesn't make sense. Causality is linked to Minkowski spacetimes. Whenever you have quantum gravity, it goes out. So this is even worse than your question of what is time.
Why I was saying that the two picture, not the what you have the two directions, one action.
Yeah. In these models with the sign. No. Well, but there are solutions which are quite plausible to that question you raised. There are some choices in this mini superspace which are very nice.
Usually when we add, like, if you have 2 degrees of freedom, okay, you have a field and a matrix. But if you add another thing, things usually...
Another approach, which will be nicer, I mean, coming from particle physics, as I do, the most embarrassing point is that the gravitational field is linked to the structure of space-time. You could disentangle this, so you have gravitational field as a fluctuation field over space-time. So you will keep this in a fixed background, and then the rest is just fluctuating fields. One of them is gravity and so on. But this approach is not consistent with the last data, which tells you that speed of propagating of gravitational waves is the speed of light. So these double metric models are not very popular now because of that. So it seems that nature prefers to keep having a gravitational field attached to the space-time structure. And we can do nothing against that.
Another thing is the constraints. Like, we have classical constraints, and then we impose our classical constraints on our quantum states. How consistent is that? Because sometimes we have a T mu that's 0 classically, but it's not necessarily 0.
Yeah, you have anomalies. You have anomalies.
So can we consider theories with where these constraints are not so stringent?
Well, I mean, this is a very subtle problem, but there are many examples. First, there is a problem. I mean, we have only a few hours here, and I'm open to discuss with all of you, but we have few hours, so we cannot touch all subjects. Even if I discard many subjects at the very beginning, even now, as you see, I'm skipping some problems. There is a very hard problem here, which is the ordering problem. So because, these theories are non-linear, you have pi's and j's, and they do not commute. So in which order you plug this thing? I just was hiding this, saying, Schrödinger operator. I took the Schrödinger formal ordering, and that's it. No? Schrödinger ordering is this one. Yeah, I think now it's... So, here there are many things which do not commute, derivatives, metric, and a lot of things. But this ordering is what I call the Schrödinger operator. So one ordering solution, which in path integral terms is transformed into the Ito or Stratonovich ordering in the discretization of time. But anyhow, let's agree. So the constraints have the same problem. And depending on how you fix the ordering, for instance, here in gravity you have two constraints, H and Pi, okay? They should commute. Otherwise, you are in trouble. You cannot impose both at the same time. And this commutation depends on the ordering. So sometimes there are problems. But let's be positive. There are solutions which do not suffer that. For instance, in 2+1 dimension, this was addressed by Aztecar in the 80s. There is a nice paper, PRL, where he found some incompatibilities between the constraints we are discussing in 2+1. But this could be arranged. Later on, it was arranged. So in that case, you have no possibility of quantizing, because one of the constraints cannot be implemented. You have to choose which one you prefer and so on. So this is another problem. But usually in gauge theories, this problem is not a real problem because you have only one constraint, and you solve it. In that case, there is no ordering problem. It's interesting. By the way, in the problem set, there are a few questions about the commutation, not of the constraints, but of the Hamiltonian and the linear momentum, which is essentially the commutation of the constraints here. But not only in this theory, but in a more complicated theory we will see tomorrow.
There is another way of, I don't know if it's more general, it's another kind of ordering that gives a Klein-Gordon loop to the Wheeler-DeWitt equation. That's what I was referencing, that there's people that, because there is a Klein-Gordon structure, you can have a normalizable wave function.
But are you working in a splitting of time and a space like?
Space model for different ordering. But then the argument is because...
But you need a minus sign in the metric, which you don't have in a space like. Klein-Gordon needs to have some coordinate, which is time-like, right? But the metrics here, the Wheeler, the DeWitt metric is strictly positive. You have no minus sign. Okay, you can show me later because it's getting late. Is there any other question, general one? Yes, go. But since you are in the last row, please speak louder.
We have written some functional differential equations, like the Klein-Gordon function. Do we have a mathematical theorems that guarantee that the solutions exist and are unique for the function?
No. They are not unique for sure, but the systems, it depends. So if it is a trivial Klein-Gordon one, yes, but if you have a metric, so if you have some nonlinear terms, then there are no, as I said at the very beginning, if you have a Klein-Gordon system, scalar field, for instance, here, which this can be reduced to that question. And if you have a lambda phi 4 interaction, even the classical theory has a lot of singularities. So it's not true that only a problem of ultraviolet divergence appears when you are in quantum theory, also in classical theory. If you have complicated interactions, you have singularities. And then this stops you for searching a proof of existence of a solution. You have first to solve this singularity problem, and then you can answer yes or not. But I cannot tell you. You have to show me the equation you have, and because there are a lot of mathematical theorems, but each one applies to a specific situation. You can. So this is the Polyakov approach to mathematics. He said that mathematics is not physics because everything in mathematics is not stable because the theorems depend on very subtle requirements in the hypothesis. If you perturb a little bit, the theorem goes. So the same happens to the question you raised. It's existence of solutions, no? But Klein-Gordon without any interaction. Without any interaction. So this is a classical theory. I mean, are you referring to Klein-Gordon equation like this one? Yes, but then it's Klein-Gordon. Yes, in infinite dimensions, you mean. But then it's not the mini superspace. No. There are theorems, I know, in functional equations in infinite dimensions, but they are very, very restrictive. So they are not very general. These theorems appear in another approach to quantum theories, which is functional renormalization group approach, exact, which at the very beginning I exclude from these lecture sets. But there are theorems which tell you which equations have solutions, which not. But they are very specific, and very hard theorems. There are papers by Bridges and some other people who have specific theorems for this infinite dimensional. And in that case, it's covariant, so it's Klein-Gordon-like. Well, no, this is very hard. You mean to have a fixed point organization group. As far as I know, the only thing which has been done is numerical work. And this, since you have to cut, I mean, you have to make a prescription for the functional and then run. But then, because at any run, you generate much more terms in the effective action, you have to cut and then fit the effective action which better accommodate to your numerics. And then this, is out of control, so I cannot tell you. And of course, there are no theorems on this. But the evolution, yes, there are for the evolution there are theorems by mathematicians.